All right. Happy Thursday. I've got a couple more things to cover on trees here, and we're actually going to rip off the book here a lot because there's two important pieces to trees we haven't talked about. So, two attributes of trees, right? Not only are they recursive in nature, but some of the ways that you talk about them are the height of a tree is how tall it is, right? How many generations there are in a tree. You might talk about height, so that's a way to describe the particular tree. And then another way that you might talk about the tree is the depth of a given subtree, right? A tree that's part of a child, something in here, the depth. So the depth is how many levels there are up until the root, until there is no more, right? Although the very top of the tree. So depth is how many parents and generations there are up to the beginning, and height is how many generations you have from the top down. And you can also, because they're recursively defined, we can talk about trees rooted at any of these positions. So I can say, hey, when we did our mammals example, right? So mammal is a tree here, mammalia. So we could say the tree rooted at mammalia. And that tree has its own height and depth. That was a little harder to figure out because it has other parents. So because if you want to stop here, it's a little trickier. So generally it's easiest to just go all the way up until there are no more parents. But our current tree, we don't have a way to know who your parent is. So if I were to pick a particular tree and ask it what its depth is, we have no ability to work our way up the tree with our current tree structure. I could start somewhere at a tree and find all the children, find all the children, find all the children. We could calculate the height of a tree currently because I can find my children, right? So the kind of the mathematical approach for that, it's the maximum height of any of our children, right? Find out the height of our children, and then we'll just add 1 because I'm this one. And then we'll do the same thing. We'll find the maximum height of all of our children and add 1. So if you think back to our Fibonacci example, adding up 1 a bunch of times is really slow. That's not ideal. We don't want to have to add up 1 every time and then find out which 1 plus 1 plus 1 plus 1 is the max. That's not great. So if we can work our way up and find our parent, that works out well for us because then we can, what we want to do is we want the maximum depth of our children. Because depth is pretty easy to calculate, right? It's just working my way up to the top and I'm done. That's fine. So if I find the maximum depth of my children, it works out pretty well. So we're going to add a reference here in our tree structure to our parent. It might be none, right? So some trees eventually don't have a parent, and that means you're the root of that tree. You have no parent here. But then when I go and add children here, I'm going to say self.parent is parent. So we have an item, and we'll have parent equals none. So you tell me who your parent is when you make the tree. We'll assume it's none unless you tell me otherwise. So now when I go and add children, I'll add the item, and then the parent of this child is self. Right? Self is the current instance that you're calling add child on. So this starts to get a little funny looking when we look at throwing self in here. But what that means is when I say kingdom.addChild, it's essentially throwing kingdom in after this item here, right? It's passing kingdom, right, as the parent here. But we don't need to tell it who the parent is because we have self. We have who you're acting on. So if you're going to add a child, you must be the parent because this is your child now. So we don't need to tell it who it is. But we're taking advantage of self here. So we can get children, we can get the depth, we can depth the up by generation. So now we'll be able to work our way up a tree to figure out what our depth is. So to find the depth of a given location, right? So we can define get depth of a given tree. We can say, hey, if my self.parent is none, we can just return 0. Right? There is no more parent. I'm level 0 essentially, right? If it's not though, if I have a parent, then I need to find who my parent is and ask my parent to find its parent and find its parent. So we can return 1 plus get depth. Self.parent.get depth. So this one is going to add 1 and add 1 and add 1 and add 1 a bunch of times, but it's not going to do it for all of the children. It's just going to follow that singular path up the hierarchy. So who's your parent? Add 1. 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 A bunch of times. As many levels as we have in here, we'll get our depth here. So that works out relatively quickly here, right? So we get 0 if you have no parent. Otherwise, ask your parent to do the same thing and add 1 to that. Right? So for each of these, then we should be able to go through and get the depth of a tree. So let's see, we're printing self item. I want to be able to print the depth here. Maybe we just go through and for each of these children. Let's have trees here. Why not? There's a list. And then I'm going to make all of these. I'm going to add them to our trees list here, just so we have them here. And then we can loop through our trees list. That might be easiest. Append kingdom. And then we'll add chordata. And then we'll add mammalia. Just so we can loop through all these things here. I think Carnivoria, Rodentia, Spiridae, okay. Oh, so we don't even have Marmota, but that's fine. We could get that one if let's get that one. So then we have Marmota is my Spiridae dot get child of 0. And then we'll add Marmota here. Right. Then after you go through and print all these, you can say for tree in trees. I'm going to print tree.depth, get depth, and maybe the tree.item. Item. So let's do this as a nice little formatted string, right? So here's the tree item. It has a depth of tree.get depth. So we should see all of these here, right? Do I need more? Oh, end the quote. There we go. Okay. So Animalia, 0, right? This is the root of the tree. Chordata has one generation above it. Mammalia has 2, right? Carnivoria has 3. Rodentia has 3. Sciridae has 4, and Marmota has 5. Does that seem to follow what we were drawing out here? Right? Because if you follow up the path, Marmota's parent should be Sciridae. Sciridae's parent should be Rodentia. Rodentia's parent should be Mammalia. Mammalia's parent should be Chordata. Chordata's parent should be Animalia, the kingdom. So we can look at this depth here. So if we were to look at this entire tree, we say the tree has a height of 5. It has 5 generations here. For some reason, you don't count 0. I don't know why. Like it's just a 0 height tree. It just has one item. Like we always start counting with zeros. So I think that makes sense. So the slow way of doing this then, if we wanted to find the height, right, the bad way of getting height here. So get height bad. That not even make any sense? We want to get the height of all of our children and ourselves, and then find the maximum value of that. So I could make a, have to go through, let's see, so we need to get the depth of each of our children, and then return that, return the max. We want to get all of our children. So we need to recursively go and get all of our children and find the children's children and find the children's children's. I think we can do that. Let me go back to the book here because this has it in here. This is why we're going to steal off the book. Our general tree, general trees, more trees, trees. Oh, there's an interesting idea. If you're a leaf, it means you don't have any children. So leaves in our tree have no children, right? They just have their item here. Otherwise, you can get their children out, right? Where's our depth here. Yeah. So 0 or depth of the parent, right? This is kind of what we did here. He goes about it a little bit differently using this position idea. That's okay. I think we can avoid most of that. Yeah, so here's the height. So the height is the max of the depth for every position in self positions if you're a leaf. And this is a private helper function here. So this self positions lets you iterate through and get every position out of the tree. So we did like a depth first. We just printed this sort of traversal. There's a way you can actually give those items back with the self positions. So we can steal that one from him because that's useful. Here's our positions. Length, root, empty. Do we not have? It's not done yet, is why. Okay. I hate his examples sometimes. He doesn't actually give you all of these things here. So we don't have a positions function currently. Yeah, he doesn't even write it. Okay, that's obnoxious. Later on, you can give these positions back, and it works out a little bit nicer. There's some other keywords we'll use. Yeah. Oh my goodness. Back to my friend. Thanks for donating to the scholarship fund here at the University of Michigan Dearborn College of Engineering and Computer Science. Appreciate you. All right. So if you want to get every position out, he has a get positions, right? That's fine. We'll go borrow his. Did he not write it in here? He doesn't even write it. All right. So this is our bad height here, and then it has a private helper function. Get height bad. So let's go and add. What do we do with this one? We added ourselves to a list, right? Took all of our children off. Yeah, I think we can go out this way here. Okay, yeah, we don't even need the helper function. So if we can loop through and get all of our children here, and get the children's children, eventually, instead of printing the item here, we're going to take our list of depths. Here is a list. We'll just append that item's depth. We'll say current item, so our depths, append my current items, get depth. And then when we're done, we're going to return the max of depths. Right, so this is the bad approach, to ask every single child to figure out what his depth is, put them all on a list, and return. So we didn't even add that optimization. We could add in here whether or not we're a leaf, because we can ignore things that aren't leaves. Because if you have children, their depth will be greater than yours, right? So we should just not even bother dealing with yours. So we can add that in. We can have a define isLeaf function that returns. So to find out if you have any children, right, that should be the length of our children list. So if our length is 0, the length of self.children is 0, then you're a leaf. If the length is not 0, then you're not a leaf. We'll return false. Right? So we're just basing all this off of length. So then we can even check in here and say, if my current item is leaf, then we'll append it. If not, we're just going to ignore it because it doesn't matter. We know you're going to have a greater item later when we go get to your children, right? So we'll go and get all the values, eventually give us it back here. So we should be able to get height then of a tree, and then we can say with a height of tree dot get height bad. Now this will work for any tree rooted anywhere, right? Because it's only looking at that tree plus its children. So when we get to Marmota, the height's going to be 0 because it has no children, right? That's okay. Let's give this a run. So we're going to see these numbers be like inverses here, right? Animalia has a depth of 0 but a height of 5. Uh-oh, Chordata has a height of 5. Oh, we're going. Ooh, that's different. Carnivoria says 4. All the others say 5. That's really interesting. Tree get height bad. How did that even work? Add ourselves. Add the children. It is a leaf. And the depth. now I'm super curious. I expected these not to get these numbers. That's really neat. Oh, okay. Sorry. So the get depth here, right, it goes all the way back up to all of your parents. That's why they're all 5, except for Carnivoria. So Carnivoria here is a child of Mammalia with its own children. Oh, feline and Canidae. We didn't add those ones. Bummer. So the tree rooted at Carnivoria, when we go get the depth of itself and all of its children, here is just 4. Right? Is that the max depth of Carnivoria's children? Because Carnivoria has the 2 children for Felidae and Canidae. So let's go add these. So we'll have Felidae, Carnivoria, get child, 0, and then we can go add that to our trees list here. Felidae, and then same for this one. Canidae equals Carnivoria, get child of 1, and then we'll go add Canidae.